Welcome back to Summarize Science. Today, we're diving into a paper about a fascinating new material that can literally toggle its stiffness on command. It's a type of smart material called a mechanical metamaterial, which gets its amazing properties from its structure, not what it's made of. The basic building block of this material is called a unit cell, which has a curved beam at its center. When you pull on it, this cell snaps into a new, stable shape, kind of like a pop-up toy. The researchers found that these two states, which they call state 0 and state 1, behave very differently. When pushed from the side, state 0 is relatively flexible. But after it snaps into state 1, it becomes significantly stiffer. Counterintuitively, the material is actually stiffer and it's taller, snapped-through configuration. So, why does this happen? The secret lies in the small support beams that connect the curved center to the frame. When a side force is applied, these supports don't just push on the curved beam, they also twist it. In the flexible state, this push and twist work together, allowing for easy deformation. But in the stiff state, the push and the twist work against each other, creating a blocking effect that resists bending and makes the whole structure much more rigid. The researchers showed they could control this effect by changing the design. They experimented with different support beam thicknesses and even added tiny, flexible hinges in different locations. By 3D printing and testing these different designs, they confirmed their computer models were correct. Each design showed a clear and predictable jump in stiffness when switching from state 0 to state 1. To show off the potential of this discovery, they created a real-world device, a monolithic soft clutch. A clutch is something that engages or disengages parts, and this one does it by changing its stiffness. It's monolithic because it's printed as a single, complex piece with no assembly required. The device has multiple unit cells connected to a central shaft. By individually snapping these cells into their stiff state, they can increase the overall stiffness of the clutch in discrete, predictable steps. It can have 4 different levels of stiffness just by toggling its internal switches. So, let's recap the important points. Researchers have created a material whose stiffness can be switched discretely between 2 states. This effect is due to the clever internal geometry that controls the interplay between forces and rotations. This could be revolutionary for fields like soft robotics, allowing robots to be soft and compliant one moment and rigid and strong the next. Imagine adaptive structures that stiffen to withstand high winds, all without complex motors or electronics, just by using the material's built-in intelligence.